Okay, good afternoon. So we've covered pretty much all topics of circuit analysis. Today, I want to cover electronics manufacturing and packaging. Okay, so it's a long list of slides, right? We're not going to. I'm going to do an overview of what it is. Everything, everything may not be possible to be covered in the 50 minutes that we have, but we'll try to hit the main points. Okay, so electronics manufacturing and packaging. So let's say let's say we are working with a desktop motherboard, right? How many of you have seen the internals of a desktop? Just 1, 2, 3, 4. Okay, hopefully there's plenty of people. So let's say this was the main board of the motherboard, right? So these main boards or these main structures, which like a large PCB, it has a big CPU that you mount on it. There's some space to mount memory sticks on it. And then there are different slots. There are empty open slots where you can connect your graphics card, for instance. There are external USB ports, external drive connectors, SSD drives that can go in there. So that level of packaging or assembly is on a system level, right? We are connecting a circuit board to another circuit board, whether it's via a flexible ribbon connector, like in a laptop, or whether it's like straight card insertion inside a main board, like in a desktop. Nowadays, even the, if you have a laptop that can be repaired, if you open up the back panel, you can see even the batteries are connected via flexible ribbon connectors. So even that sort of system to system packaging. And then each PCB has multiple components that are mounted on it, right? And you have done some soldering of components on a PCB this quarter in 143, I believe, right? And so that's a level that's slightly, say it's level 2, but I would say it's like a slightly higher level because you're going into the miniaturized version, right? So we have all these systems that are mounted on one PCB on a printed circuit board, and you are making these connections. So that's board level assembly or board level connections. Then there is the chip level. The chip level means you're taking microchips, and those microchips, fabricated microchips, are encapsulated inside a epoxy structure. And that's a chip level packaging. And finally, we have wafer level packaging. The wafer in here refers to semiconductor wafers, typically created out of silicon. So it's silicon wafer. All of these are created from silicon semiconductor material, hence silicon wafer. And the reason they are called as wafers is because they are round in shape, very thinly sliced. Okay, I had a few wafers in my office. I wanted to bring them show and tell, but in my rush to get here, I forgot. So hopefully on Monday, I'll remember to bring those in for show and tell. So there's 4 levels of packaging. What we are going to look at is the first 3, 0, 1, and 2, not the last one, not the 4th one. Okay. All right. What is this? What the heck? That's interesting. Controls are missing. All right, sustainability. Right, sustainability is a topic that all engineers in today's world should at least be familiar with. And so there are 4 E's of sustainability that are defined by Houston and Gibson. Okay, environmental, energy, equity, and economy. So the references are right here. First published in the mid-90s. I would strongly recommend that students do check it out. As graduating engineers in about 3 to 4 years, this will be a big part of your working career as an engineer. Okay, this applies to all fields of engineering. This actually applies to all fields, no matter whether it's engineering, scientific, or any other. If you're living in today's world, sustainability is a big topic of discussion. And sustainability means living and engineering with a sustainable manner, such that the environmental and natural resources are replenished. So you design a system, the system is going to consume some resources. Those resources need to be sustainable, meaning the resources need to be renewed and not being completely consumed up. And that's one of the big things in today's world. So some questions to ponder about each one of those E's in ecology. What natural resources are required for your system, right? What natural resources are required? What ecological impacts will your system have in its environment? Okay. How does the process impact the environment? How does it impact other species? Energy is kind of a given. Everything that we do nowadays consumes a lot of energy. And so what kind of energy and how much energy is required? Can that energy be used with sustainable or renewable resources? There's this larger discussion in the world that's between renewable and non-renewable sources, right? And no matter which side you fall on this, we know that the fuel that we are using, fossil-based fuels that we use, are finite in resource. It takes thousands of years, hundreds of thousands of years to create those. So if we are talking about like thousands of years in time length, then yes, we can say those perhaps could be renewable, but not in our lifetime, right? The resources that we are using up right now, fossil-based fuels, are basically were created over hundreds of thousands of years. So in our lifetime, they are not renewable. Once we use them up, they're gone. That makes sense, right? So they are not renewable, they're not sustainable. On the other hand, there's wind power, there's solar power. Solar power is, well, for all intents and purposes, the sun shines every day. You have a few hours of sunlight, depending on which part of the world you are, essentially free, right? So you install solar panels, that kind of energy is renewable. That also has limits. If you want to store that energy, then we need some sort of storage mechanism, which are in rechargeable batteries. Those rechargeable batteries are charged during the daytime and then use the energy at nighttime, right? And so in many parts of the world, in the US and California, they mandated it. So solar energy is very common. Many other parts of the country, it's not so common. But many other parts of the world, it is actually, in fact, very common. So in small towns and villages across many of the Asian countries, in Africa, in Europe, where the sun shines down in plenty, solar energy is very widespread. And so technology has advanced so much where previously people had to worry about obtaining power line connections. But now, with the advancement of technology, you have skipped a generation where power connection is not required at all. You could be living off grid completely. For examples, in today's world, there are people living off grid, meaning they have no connection to a power utility company, and they are just surviving on solar or not surviving, living on solar energy or wind power energy. Okay, so that's an example of sustainable energy. So what kind of sources provide that kind of energy? Should be solar and wind. There's also hydrogen powered, but it's not taken off as much. Economy questions to ask about a process. Well, that's always a deal. If your If your system, your application, your solution does not make a profit, does not generate a profit, then companies are not going to work. Companies are not going to support that system. Okay. So economic results impact people, financial, actual capital that is required to actually implement those systems, and of course the natural capital, which again goes back to ecology and environment. And then finally, equity. Who does the process and its derivatives impact? Meaning, if you are implementing a system, how is it affecting? How is it affecting the people, the environment, and who are the stakeholders? Any kind of system in the world, it would be very hard to make it equitable without actually giving it, due consideration. So these are the 4 E's that we need to keep in mind. Okay, PCB fabrication. You've all worked through it, right? You worked through it. You've created your PCBs. Hopefully they worked. There are some issues, but it's part of the learning process. That's why we are here to learn. So PCBs are nothing but they are wires that are connecting components. Okay. So if you take a battery, connect a resistor with a wire to it, powering an LED perhaps, and you take that and you create a 2D or two-dimensional layout, that's what is a printed circuit board. It is literally, it looks like a print, and hence this one is a printed circuit board. So it is nothing but a connection of components that are connected by wires. So basically there are conductors, there are wires running from one point to another point in a board, making connections between different components. As a matter of fact, when I get to talk about ICs are nothing but micro versions of a printed circuit board. Okay, integrated circuits are nothing but miniaturized micro versions of a printed circuit board. They're simply components that are connected by different wires. So a printed circuit board is basically a collection of components connected by wires. And so there's a substrate or a base where we work with, and the connections of wires is basically a two-dimensional structure made up of some sort of conducting metal. Typically, it has always been copper. Okay. Silver is not as common, but gold is actually very common. Gold is one of the best known conductors, does not corrode easily. It maintains its properties over a long period of time. And when used in small amounts, it's economically viable. Okay, so gold is a very common use in the electric and the electronic industry. So PCB is comprised of several layers of material. We have the substrate, which is right here, and then you have the conductors running on top, and these would be either some sort of copper or some sort of gold. And you have solder masks, and you have inks to actually transfer your mask onto your board. Multiple purposes, indicators, quotations, names, numbers, values. You've used, I believe, you use Fusion 360 software to design something like a 3D model of a packaging. And then you might have used, did you all use Eagle in the lab? Okay, great. So you have experience with that. OrCAD, we have an OrCAD license. I don't know if that worked or not, but those are the common softwares that we use to design PCB layouts. When I was a student, and this is obviously like 30, 35 years ago, a long time ago, we designed like simple PCBs. We just drew them by hand. We had like a printed ink in a pen, and we simply drew it by hand on a simple circuit board, very small one. And then, of course, for larger, complicated ones, we outsource it to like a local company, and they would actually take our designs and create them. And now it's incredibly easy to actually get it done. Simply upload your designs and the software and the companies take care of everything. All right, design rules check, PCB design manufacturing. I'm gonna skip through that. Skip that. Oh, I do want to mention this. If you ever see this on a PCB, it serves a purpose. Such a large amount of metallic copper can serve as a ground plane, especially when it's like RF circuits like antennas. It provides a reference path or reference point for all antenna signals to converge it and provides a path to ground, a common pathway. Also, obviously helps with heat dissipation, right? You're spreading everything out. All right, PCB manufacturing, you have these large panels. They're cut down into individual panels. You can see big ones. And then holes are drilled. You create vias, VIA, you create vias in the structure. These vias, in my time when we were doing this, they were single-sided PCBs. So we just worked on one side of the PCB. Now, obviously, with increasing complexity of circuits, you have components mounted on both sides. And then came with like surface mount devices and through-hole devices. I typically work with like through-hole devices, which we still use today in breadboards and create our circuits. The way we transfer these patterns or our patterns of wires is by taking a material known as photoresist. Photoresist is a material that resists the transfer of photons, so light. It resists light. And photoresist is very common in the IC and PCB manufacturing industries. It's liquid chemical, and then we spread it all over the surface of a printed circuit board. And then, like a photographer's darkroom, we expose the pattern that is on a glass mask onto our PCB. Areas that are exposed can either get washed away or can harden. If they get washed away, they are known as positive photoresists. If they harden, then they're known as negative photoresists. So in the slide here is an example of a negative photoresist. If you've ever heard the word the film negative, like film cameras, and they use the word term negatives, the reason is because it creates the opposite pattern when light goes through that film. Okay. And so the pattern is transferred in a process similar to a photographer's darkroom. And a negative imprint is created. If you use a positive photoresist, you would have the exact same print. So positive resist replicates the print. I'll explain. So let's say this could be a glass or a plastic film. Okay. And I'll bring this class on Monday. So this is either made out of glass or some sort of plastic film, right? The transparent areas that you see here, or the white areas that you see here, are transparent. Okay. And these are obviously blocking the light. All right. So now let's say you take this plate. You take this plate and you put it right on top of your photoresist coated sample. Your sample is coated with photoresist material. You take this plate, you put it on top, and you shine UV light through it. The light will be blocked in some areas and it'll be allowed to go through in the transparent areas. The areas where the light goes through and hits the photoresist is going to be affected. If it's a positive photoresist, the light affected areas are going to be etched away or removed. So what is left behind on your photoresist are the areas where the light is blocked, which is your pattern. And so you get an exact replica of this plate on top of your PCB. Does that make sense? A negative photoresist, everywhere the light hits is hardened, and everywhere that is blocked gets washed away. And so areas that are blocked, like these, areas where the light hits will harden on the surface, and hence you get the opposite pattern. Light goes to the transparent areas, hits the photoresist, and it hardens on the surface. Areas where the light does not reach, meaning the areas that are blocked, like this one, for instance, is going to get washed away. Hence, it's absent. So now you get an opposite image or a negative imprint. Hence, it's known as negative. And then, like a photographer's darkroom, we take these exposed samples, we stick them in some chemical, and it develops. It either etches away or washes away the etchant. Did y'all do that in the lab, by the way? Or was it sent out? It's sent out. I actually did this when I was a student. So you have copper, and you take like a beaker, or you take like a big beaker. Our PCB was this big. And we take ferric chloride. I still remember, somewhat like dirty yellow in color. Ferric chloride chemical, you put it in a bath, mix it with water, create your solution, and you stick your PCB in there. The photoresist is going to protect your copper based on the pattern that you developed. So the copper which is exposed gets etched away or eaten up by this ferric chloride etchant. So it etches or eats away copper. And that's how you get the pattern that is transferred on the PCB. Anyway. Solder mask, electrical testing, PCB assembly. PCB assembly is soldering, which is basically what you've already done. You have through-hole components, you have surface mount devices, SMDs, and there are multiple ways to do it. Through-hole ICs, by the way, what we see here is simply a package. The actual chip inside of this is not even this big. Probably less than 1 millimeter in size. Okay, so the actual chips that we see are encapsulated inside this epoxy packaging. The actual chip is very, very small. Okay, surface mount ICs, different factors. Soldering is how components are attached to the board. Solder is made up of some sort of metal. Commonly, it's made out of tin. And you can see a through-hole joint. This is the solder material. Okay, and an SMT joint goes from the top, does not go through the board. Advantage of SMD devices is that you can have devices mounted on both sides, plus they are very small. Now, obviously, we don't want lead in there. So I'm gonna skip over this. There's a stencil. Reflow oven. We, by the way, do have a reflow oven in the SPL. So if you have never had a chance to use it, definitely do check it out. What I want to talk about is integrated circuit fabrication. So, talked about how PCBs and ICs are the same thing. Okay, PCBs and ICs are the same thing. PCB is basically simply a board that takes your components, and it's a place for you to connect wires, make connections for your circuit. So you could create a circuit on a breadboard. The breadboard clips are making the connections. You could connect them with wires, or you mount them on a PCB. So this was in the late 1940s. The first transistor ever was actually demonstrated by three people: John Bardeen, Walter Brattain, and William Shockley. Those three ended up winning the Nobel Prize a few years later for the invention of the transistor. And then a few years later, they presented the first integrated circuit. It was actually two simultaneous demonstrations, near simultaneous demonstrations around the 1950s. Jack Kilby of Texas Instruments is now credited with being the first one to do so. He independently displayed a working prototype of an integrated circuit, Texas Instruments. Okay, and he ended up winning the Nobel Prize like several decades later, like in the 2000s. Okay. Anyway, the demonstration of this transistor and this integrated circuit, two separate things, they are the ones which propel the semiconductor industry to what it is today, right? So the name integrated circuit comes from the fact that you have all these components. You have these transistors, diodes, resistors, discrete components separately. But if you grow them all at the same time, you manufacture them all at the same time on one single piece of semiconductor material, you're integrating all of these components together. So you have a circuit connected by wires. You mount them on a board, you get a PCB, printed circuit board. Now, if you take a piece of semiconductor material and you integrate all of these components all at once and you manufacture them all at the same time, you get what is known as an integrated circuit. So you have a discrete circuit created on a breadboard, you mount it on a board, you get a PCB, and you create it on a single piece of semiconductor material, you get a IC. One of the earliest successful microprocessor ICs was created by Intel, 4004. Then they created many multiple versions. There was a microcontroller called 8085. When I was a student, I learned assembly language programming on there. 8086. Then came the 80286, 486, and 80586, which, because of 5, came to be known as the Pentium processor. And that's the architecture that we use today. Integrated circuit design is one thing. Integrated circuit fabrication or manufacturing is a whole different process. There's an entire industry devoted to it. And recently, they all came to a head and in the general consciousness of the general population because of the chip shortage that occurred during the pandemic. So you hear about these companies that say, okay, they're making their chips. Like Apple is making their own chips, or Qualcomm is making their own chip. Samsung, Intel, they're making their own chips, right? None of these companies that you hear, NVIDIA, AMD used to, but not anymore, but AMD, NVIDIA, Apple, Qualcomm, none of these companies know how to make chips. Okay, they design chips, and even the design comes from a small British company known as ARM. ARM is for Advanced RISC Machines. It's a British company, and it has a licensed architecture that they sell to all these companies. They buy the license to use these architectures, and they create their own chips. So they design these chips, and when they want to manufacture them, they go to companies like, well, Intel used to design and manufacture their own chips. AMD used to design and manufacture their own chips. Samsung Semiconductor used to design and manufacture their own chips. But all of these companies, NVIDIA, Apple, Qualcomm, they go to these foundry manufacturers that actually make these chips. Most of these foundry manufacturers are now located in Taiwan. As engineers, this is something that's very important to you because of the chip shortage that occurred, it brought all of these governments, it made these governments realize, all countries realized how important they are to the functioning of the economy. Because chips go into every tiny appliance or consumer device that we use nowadays, from the most powerful to the most mundane. Even a tiny greeting card that has like some sort of sounds has a tiny microchip inside. A small cash register has a microcontroller microchip inside. A typical vehicle has hundreds of ICs and microchips inside. Okay. So the manufacturing of microchips is a highly specialized process. There are tons of factories that are being opened up in the US nowadays. It's a very expensive process, very specialized skill set. And the work of creating these microchips takes place inside a room known as the clean room. You ever seen a video of people in white bunny suits gowned up inside like a white looking space? That is known as a clean room because it is in fact a clean room, because you are working, creating a PCB at the micro scale. Micro means 10⁻⁻⁶ meters. At the micron scale, even tiny dust particles that we can't see, which are in the air around us, are the size of huge boulders. So if you're trying to lay down a wire and you have a huge boulder in the middle, your wire is not going to get built. It's going to be interrupted and your circuit's not going to work. So you need a clean space that is devoid of all particles, all dust particles, where you can build these kind of microchips. Hence, that's known as a clean room. These kind of clean rooms are expensive to build. We have one here on Cal Poly, on campus, where students, and we teach a class once every year. Students can go into this clean room, we hand them silicon wafers, and we learn the steps of IC fabrication. We build our actual microchips, we build diodes, we build resistors. The students go into the clean room and we work on it every single class, every single week. And at the end of the quarter, we end up with the working silicon device. Anyway, so each of the processes that we run through for this IC fabrication, each machine costs about $10 million to $20 million. Even in an academic clean room like the one where when I went to grad school and at Cal Poly, costs several $100,000. So if it's a fabrication facility, let's say like Intel or Samsung Semiconductor, that's going to make or manufacture these ICs, a machine costs 10 million. Just one machine for one process costs 10 million. You need at least 5 or 6 of those in one room to go through a process. So that's about 50, 60 million in one room. Then you have multiple such rooms inside one clean room. So multiple such bays inside a clean room. And so that's about 50 million. And let's say that's 10 bays, that's 500 million right there. And there'll be like 2 or 3 clean rooms or multiple clean rooms on every single floor. So it's 100, 200 million on every floor. And that's probably about $1 billion invested in one big building. And you could have like multiple such buildings in one factory location. It's about $15, $20 billion just to start one single factory location. And so TSMC started working in Arizona a few years ago. That factory, I think, is about to come online. Intel is building some new ones in Ohio. By the time you graduate, in about 3 years, all these factories will need engineers, technicians, workers at all levels. Associates, bachelors, masters, PhDs, they hire a lot of people. Okay. My entire specialization, the reason I'm talking about this so much is because my entire specialization was in microfabrication and MEMS. And so once a year where we teach the class, it's under BMed, BMed 434 and 435. It's cross-listed with EE. When we get to semesters, it will no longer be cross-listed. You can take this class as a junior. You can take this class as a senior, sorry. But if you have certain prereqs done, you could take it as a junior. So if this is something that interests you and you want to go in there and work on something, you can also do your research in there. Then you want to keep a lookout. In the winter quarter, we offer that class. All right. So we create these kind of structures. This is the side view of a silicon wafer. Okay, this is a side view of a silicon wafer. So there are these videos online. If you're interested, you should definitely check it out. I'm not mandating it, but I would strongly recommend. This is an entire career pathway that people are not aware of. Okay, even if you have a bachelor's or a master's degree, Starting salaries in these positions is 100K and above, okay, or very close to 100K at least, depending on the location. Intel's main foundry business in Hillsboro, Oregon, they hire PhDs and master students all the time. So I have several friends and peer students who I went to grad school with. They work at that location. Okay, so when you create these ICs, these chips, they are very small. They are on the size of like millimeters. They're very, very small, right? And they have these interconnection pads, which are on the size of microns, right? So it's like 100 microns or 200 microns, less than half a millimeter in size. So how do we make those connections and how do we protect this chip from being broken? So again, this is a side view of a microchip. We take this chip, this is less than millimeters in size, and the top of this chip has some sort of small pad, right? And what we do is we are using these pads to make external connections right there onto that pin. And those pins are then encapsulated inside this epoxy material. And this I'm saying epoxy, but it could be any other material that's that could survive the environment. And this is basically what we actually handle, right? The actual chip is not available to us. The actual chip is inside. It's sealed. It's hermetically sealed inside this package. And if you are handling a chip, whether it's 8-pin or 10-pin, 12-pin, 14-pin, 16-pin chip, that is just the outer packaging. The actual chip is inside. It's very, very tiny and it's hermetically sealed inside. It can't be opened. Once it's sealed, once it's fabricated and sealed, it's there. And hence it says we are making connections from the tiny chip to the big pin so that we can externally use it. And it's also protecting at the same time because it's sealed inside. Okay. And so the IC assembly flowchart, this is actual microchip. So the microchip is very tiny. There are gold bond pads. These are gold bonds, and these are gold wires that are coming out and making connection to big pads, right? So you have these wires coming out. So that the process of connecting those wires is known as wire bonding. Okay, we have a very thin, fine metal wire. It's like trying to insert a thread inside a sewing needle. It's even smaller than that. So it's a very thin wire. And there are special machines called wire bonding machines. We have to actually place the wire, create some sort of, we create heat depending on the machine. There are several different methods to create heat. We create a momentary instant of heat where you actually melt that wire. And so it makes a sort of a ball joint on top of the pad. And then you pull that wire out and make another connection. That process is known as wire bonding. That is by far the most common. Then you have now the flip chip, where you take the die, you turn it inside out, and you bond it directly to the package. And so that's wire bonding right there. You create a spark melts it on top, and it creates a nice round wall, and it makes a connection on that chip right there. That's example. These are SEM images, by the way. SEM stands for scanning electron microscope. So there's an electron ion beam, and it scans the surface of your sample, and then goes through computer processing, and we can observe microscopic details inside our device. the scale here, the distance is 60 microns. This one is 70 microns. So very tiny. Interconnection tab, interconnection flip chip, encapsulation, and it's in green engineering design principles. I will leave that for students to read. Okay, as I said, today was mostly an overview of manufacturing and packaging. I like to emphasize IC manufacturing or fabrication because that's an area that students are not familiar with. Actually, most people are not familiar with. It's a entire career option that you can choose if you want to go work. And the field is highly interdisciplinary. So several of my friends and peer students, they were from chemistry, physics, chemical engineers, mechanical engineers, industrial engineers, biomedical engineers from all fields. Okay, it's a highly interdisciplinary field. The current director of the clean room here is a professor in mechanical engineering, Hans Meyer, Dr. Hans Meyer, and the assistant director is Benjamin Hawkins. He's in biomedical. Dr. Hawkins teaches the lecture class, and then Dr. Meyer, Hawkins, and we each teach one lab section where we take students inside the clean room. We teach them how to build microchips. Also, in a slightly related topic, we do offer EE 422, which is called polymer electronics. That is in a room in our EE building, but that was created and designed by a professor who's now retired. But before he left, he trained me and Hawkins on that system. But the system's not been used for several years, so it needs to be repaired. There's some upkeep and maintenance that needs to be done on that system. We are hoping we can get it up and running within the next year. So by the time you are in your senior year, you might be able to take that class. And the principles of polymer electronics that we teach in that class are the exact same ones that we use for IC fabrication. It's a very genius solution to creating a clean room environment inside a normal lab room. Okay, and so these are the things I want to leave students with, is something that you can think about. So the entire talk for today is more as information, providing information to the students. Okay, so I'm not going to assess or test students on the final or in the quiz based on anything that we have done today. But this is, as practicing engineers, this is something that is important information for students to know. Okay, whether you are in electrical engineering or any other scientific or mathematical field, sustainability is an important topic. Okay, so keep that in mind. All right, so I'm going to end class here today. If anyone has any questions, feel free to ask. Okay. All right. Well, I'll bid you a good weekend. I will see you all on Monday. We'll have a quiz on Monday based on Thevenin Norton. Again, Thevenin Norton, no analysis, but just how to set up the circuit in order to actually perform Thevenin and Norton analysis. And that's what I'll be assessing on. Okay, so it'll be rather straightforward. Setting up the circuit simply means, how do I modify the circuit in order to determine Thevenin resistance? How do I modify the circuit to determine Thevenin voltage? How do I modify the circuit or set up the circuit to determine Norton current? That's it. And so if you have a problem, you can take 5 minutes to set it up. So it's not going to be a long quiz. Okay. And that would be it. And Friday, I don't believe we'll have class. It'll just be open office hours. Students can come and ask questions, can get anything they want clarified. Wednesday, I'll just do a brief review. We have covered pretty much everything in our class. Maybe a couple of examples on dependent sources, perhaps on Monday. Other than that, we're pretty much done. I'll have one more homework for students to solve. That'll be based on Thevenin Norton, and that won't be due until like later in the week. I'll perhaps make it due like Thursday or Friday or something. So you have the entire week to get it done. Okay. All right. Have a good weekend, and I'll see you all on Monday.